Hello and welcome to this tutorial for the Weld capacity design for beam ends spreadsheet. In order to get access to the spreadsheet and the PDF worked example, you will need to go to my website and click on this icon here, and that's going to download a zip folder which has the spreadsheet inside it as well as the PDF worked example, which sort of sits alongside the spreadsheet calculations. Okay, I'm going to go in here. I've already got the spreadsheet open. And when you open the spreadsheet, you'll be met with this page here, which is the project info page. I'm not going to go into detail about all of the project info bits here, and I'm not going to cover the macros for how you save data to the save design sheets and then back and forth, as well as all of the printing macros and everything, because I've covered that in previous tutorials on my website. For example, if you go to, I think it's the Beam Designer one. It has a lot more information about how this whole system works, how you can save data in, load data back, make a summary table and so on. Okay, so I'm just going to focus on what the actual spreadsheet does in regards to the Weld design. Okay, so anyway, back to this project info sheet. This bit up here is obviously just the project information, so that's just data that will be used to fill up the header information up here, for example on a design sheet. But you'll also see something new on this spreadsheet which isn't on the other spreadsheets, and that's this bit down here, which is the calculation method for the weld effective lengths. Effectively, when you've got a weld, you want to make sure that you account for the correct length of weld when you're doing your design calculations. So what I mean by that is, if I just do a quick sketch here in Paint, if I have a weld, so I'm going to do a little rectangle here. Let's say this, the actual overall length of the weld here is L. Okay. When we actually do our design of the weld and want to find out the capacity, we need to actually reduce the length of this weld and work out an L effective. Okay, L effective, and that's the length that we're going to use to get all of our capacities and work out, how strong the weld is effectively. Sometimes you can use the full length of the weld if you know that the weld spec has been, you're going to get a full weld on there. However, generally speaking, you should be using this L effective here, which accounts for a loss of the weld at the ends of it. Okay, so the question is, how do you go from L to L effective? Well, what you do is you do L minus 2 times A. Okay, and A in this instance is the throat of the weld. Okay, now if I go to a diagram I've made earlier over here, this is a sort of cross section of a weld which is joining two bits of material together. And you'll notice here you've got the leg length S, and then you've got the throat length A in here. So what you need to do is you need to work out this throat length A and then subtract 2 of those from the length of the weld to get your L effective. However, a lot of the time people will use the leg length instead. So if I go back to this drawing here, a lot of the times they'll use L minus 2 times S. They'll subtract the leg length instead of the throat width. Okay. Now this one down here, when we subtract the leg length, is more conservative than doing this one up here. And the reason for that is that S is typically a lot bigger than A when we're looking at the dimensions. And you can see that back on this diagram here. This length S on the diagram, this length here, is clearly longer than this length here. Okay, you can see that it's right. You can form a right angled triangle here. This length here, the leg length S, is the hypotenuse of that triangle. And so this sort of short side here is obviously less than the leg length. Okay, so if I go back to the spreadsheet, what this is actually doing up here is it's saying, how do you want to generally work out this L effective value in the calculation spreadsheets on the other sheets here? Do you want to use length of weld minus 2 times the leg length, which as I mentioned before is conservative, or do we want to use length of the weld minus 2 times the throat width, which is obviously you get a bit more capacity out of that one. Okay. So that's what this is doing, and you'll notice that this propagates through to the PDF design sheet, the I section design sheet, and the box section design sheet, and specifically it affects the calculation of the weld length over here, it's L effective. Okay, so that's all that's doing at the beginning of this spreadsheet. I'm now going to jump into the PDF design and sort of give you a run through of what that's doing, what this sheet lets you do. Okay, so in step 1 over here we've got all of our forces. So we've got our axial compression, our axial tension, our minor and major axis shear forces, torsion, and then our major and minor axis moments applied to the beam. These are all applied using the Eurocode notation. Okay, so if you want some more information about the axis of all of these forces and sort of the sign conventions used, if you go to the PDF worked example, it gives you a rundown of sort of how those axes are used on the beam. But these are sort of the typical notations used for Eurocode and for the directions of all of these forces. Okay, so you can put all your forces in here. You'll notice that if you put something in for compression, nothing's going to happen. This is just included for completeness, because when you apply compression to the end of a beam which is welded, the welds aren't really doing anything there. Okay, I'm just including that there in case you've got a design and you want to include that for completeness in the final calcs. But if I put in tension, that's going to load up the welds. If I put in 45 kilonewtons, we can see that our current configuration means that the welds are 5% utilised for that axial tension case. I can continue to fill this out with a bunch of forces. We've seen here that, for example, we've put too much torsion on. That's failing by 166%. And also in the minor axis here, we're failing by a huge amount. Okay, so this tells you all of the utilizations for those forces. You can also scroll over to the right here and see in section 4, it will actually give you the capacities of the welds under each of these limit states. And I should mention as well that if you've got more than one of these acting at the same time, so let's say for one of our load combinations, we've got the axial tension and the minor axis shear acting at the same time, you would need to actually make an account for both of these together. So an easy way of doing this would be to basically sum together the utilizations. So you could see that when we apply 45 kilonewtons in tension and 10 kilonewtons in minor axis shear, would effectively be 6% utilised, right? Because 5 plus 1% is 6%. That would be a conservative approach to sort of looking at how to combine these forces, okay? But effectively, all these percentages are doing is saying how much are the welds utilised for that specific force on its own, acting in isolation, effectively. Okay, so that's what the input forces are doing. In this next section here, we can specify our PFC, our parallel flange channel. So if I change the PFC over here, you'll notice it changes the plot over here for our PFC. We can change the steel grade of the PFC in here, so S355 or S275, and then down in section 3 we can specify the substrate material, the thickness of that substrate, and the steel grade. Okay, and then the final section of inputs is this input weld information up here. So we can specify the steel grade for our welds, and then we can specify the whether to include them and the leg length. I'm just going to cover this bit here about the steel grade for a second. Let's say, for example, I had a steel grade for my PFC and for my hold on a second. Yeah, for my if I had the steel grade lower for my PFC and for my substrate, you'll notice that we get a red error message here, and basically that's because I've set a higher value for my weld strength than I'm actually able to achieve in the substrate and the PFC. Effectively, what you should be doing is taking the minimum of these two values for your weld strength of the PFC. Okay. Now you might be saying, well, why is this not automated? Why does this not just get automatically set to the minimum value of these two up here? And the reason I've done that is just to allow you to quickly toggle this value here in case you want to have a look at how the grade of steel affects the strength of the welds, instead of having to go back and toggling a bunch of things on and off. Okay. But that's why that red message is there basically. If you specified, for example, S275 for either one or both of these sections for the substrate or the PFC, then you need to be using S275 for your weld spec over here. Okay, otherwise you're going to get that error message. Okay, so the next thing to talk about is about the actual welds themselves on the PFC section, and these are plotted in red on this diagram underneath. And so we can include them or actually exclude them from the design. So for example, I can exclude the top flange and get rid of that, and it will disappear off the diagram. I can go through, continue to delete off some of the other welds. One thing you should notice though about this, and this is specific to the torsion case, the torsion case relies on the welds to the top and bottom flanges. And so if you remove the welds to the top or bottom flanges, you're going to get a spurious result when you look at the actual strength of the torsional moment. Okay, so you do need to be careful about that. You need to make sure that you've got welds for the top and bottom flanges when you're looking at torsion, because the strength in torsion really relies on these welds on the top and bottom flanges. Okay, So that's how you can specify the welds for each of these parts of the PFC. And then here you've got the leg length of the weld. And again, the leg length, if I go back to this diagram, the leg length of the weld is this dimension here in S, okay? So that's the leg length. And the values here are the typical leg lengths for the welds, and these are taken from the blue book, from the SCI. One thing to mention as well is that all of these weld capacities and everything that's shown in this this spreadsheet are reliant on the welds being at 90 degrees. So if I go back to this diagram, what I mean by that is it assumes that this angle in here, the angle between the two materials that you're welding, is 90 degrees. Okay, that basically is what the SCI Blue Book uses for their weld capacities. If I go back to the spreadsheet, you'll see these transverse and longitudinal capacities in here. These are also from the Blue Book, and again the Blue Book relies on that connection being a 90-degree angle for the fillet weld, which typically will be the case. Okay, but obviously if you're welding on some sort of crank system, or you've got an end plate which is got some kind of weird chamfer, the weld may not be at 90 degrees, and then these values here are not going to hold. Okay, so you need to make sure that you've got a nice 90-degree connection between your PFC and the substrate material in order for these calculations to make any sense. Okay, and also just to reiterate, this weld length L effective here is just the overall length of the material we're looking at. So for this 78mm here, that would be the length of this top flange of the PFC minus either the leg length or the throat length, depending on what we've set back on our project info page over here. So we've set the leg length, so effectively this 78 comes from doing the width of the section, which is 90mm minus 6mm minus 6mm. Okay, and that's how we've got that. So that's all of the inputs for the spreadsheet. I'm now going to go through all of the calculations for it. So the first two sections here, section 5 and section 6, they basically just work out the centroid of the welds in the major and minor axis, and then work out the stiffness of that weld group, and then finally the elastic section modulus of the weld group. And those calculations are used so we can work out the bending strength of the welds when we apply a moment to the major or the minor axis. Okay, so if I go down here to the first section, we've got the first chunk here, which is basically the geometrical decomposition. This just works out the centroid of the weld group about the major axis in this case. And then the second section here, the parallel axis theorem, this just works out the stiffness of the weld group. And you can see here down the bottom we've got the position of the centroid, the moment of inertia, and the elastic section modulus. And this is covered in more detail in the PDF worked example. I sort of break down each bit one by one, and there's also a diagram which shows sort of where all of these lever arms and stuff are taken from. For the PFC one, the lever arm is taken from the underside of this bottom flange here. Okay, so that's what that's doing. Again, section 6 is doing the same thing, but it's just doing it around the minor axis of the weld group, so around this pink dashed line rather than the blue dashed line, which would be the major axis. Okay, so that's what these two sections are doing. The next section is when we go on to working out our actual weld capacity. So we have the capacity in axial tension, and you can see what I've done here. Basically I've got each weld on the PFC is decomposed out, then I have how the actual load, so in this case axial tension, how that's actually loading the weld in each instance. So for axial tension, that's just pulling on the section, and so it's putting every single one of those welds into a transverse loading. And in case you're unclear on what transverse and longitudinal means, if I go to a diagram here which shows a 3D, our transverse direction would be applied like this, which is perpendicular to the weld, and our longitudinal direction would be applied like this, which is along the weld. And again, those two sort of definitions are given more information in the PDF worked example. There's a little diagram in there which shows that a bit better in a bit more detail. Okay, so we get our direction that the load is applied in, we get the length of our weld, which we already defined further up in section 4. Then we work out our weld capacity when it's being loaded transversely. We multiply the weld capacity by the weld length to get our total capacity when it's loaded transversely, and then we just sum all of these together to get our strength of the entire weld group when subjected to axial tension. Okay, so that's what the case for axial tension is doing. We have a similar situation for the major axis shear and for the minor axis shear. The only difference is that some of the welds are loaded longitudinally and some of the welds are loaded transversely for these situations. Okay, and you can see that if I just do a quick drawing here in Paint again, just do a new drawing. If I have the PFC like this, and I'm loading it in Shear, then clearly this top flange here is being loaded transversely. This bottom flange welds are being loaded transversely, and the welds on the web, well, those are being loaded longitudinally. Okay, and it's going to flip round. It's going to be the opposite for when we load in this direction for the minor axis shear. Okay, so that's all that's doing. Go back to the spreadsheet. So that's the major and the minor axis shear done. The final two sections here are section 10 and section 11, where we look at the major and the minor axis bending. And all we do in here is we're working out the strength of the welds, but it's expressed as a stress. Okay, so all this is doing is basically taking the weld capacity and dividing it by the leg length, okay, of the weld, and then we're just multiplying that by our elastic section modulus to work out our bending moment capacity of the weld group. We do that in the major and the minor axis, and we work out our bending moment capacity of the group of welds. And then finally we have the check for torsion, and as I mentioned before, this is a simplified check for torsion. It basically just looks at using the welds on the top and the bottom of the PFC. So if I draw that again for you, we have a PFC, we have some welds at the top, up here, we have some welds at the bottom, down here, we have a torsion moment applied, and we're saying that the torsion moment is resisted by a longitudinal force in the welds, like that, top and bottom. So that's what these calculations are doing here. Okay, it works out the strength of the welds longitudinally, and then multiplies it by the lever arm from the centroid of the section to the centre of the top flange. Okay, so that's all that's doing there, and that's the entire check for the PFC design effectively. It's very, very similar, these set of calculations, for the I section design, okay, and for the box section design. Effectively all of the sections are the same. You've all got sections 1, 2, 3 all the way up to section 12. They're all sort of labelled the same, they all have the same things going on. The only difference is you've got some slightly different inputs at the beginning. So for the I section down here, we have whether the section is a rolled or a plate welded system, and the only difference between these two is for a rolled section you've got little radius corners in here. So if I go back to my drawing, a rolled I section effectively has a curved corner in here. If I just draw this again, so I'm talking about this little radius in here, in here, in here, and in here, and it basically eliminates this corner from our weld. So our weld flat face will start from this point here, these points here, and we ignore the radius corners on our welds, and so our welds are in sort of this space in here. Okay, for a plate welded section we don't have that, it's just a series of flat plates that are welded together for an I section, so we don't have a radius at this point, so our weld can go right into the corner there. Okay, so that's all the difference what we've got here. You'll notice that a rolled section will give you more capacity than a welded plate section, plate welded, will give you more weld capacity than a rolled section. You can see that up here. If I just toggle these two values, if you look at this section 4.0 star, you'll notice that the values get higher and lower as I toggle between these two. So that's sort of the only difference that we've got for the I section design. The final section design is the box section design, and the only difference that we've got here is we've got a forming type. So the forming type, we can either have a hot rolled section or a cold form section. Effectively, the only difference between these two is how big the radius is on the corners, and you can actually see that being plotted here when I toggle between the two. The cold form section has bigger radiuses on the corners because of the manufacturing process, and so you've got less length of weld that you can get on the flat surface. So the hot form section is going to give you better capacity. And then finally we've got this section orientation thing here, and this is just a simple toggle button to make it a bit easier for you to flip around the axis through which the bending is being applied. Okay, and that's basically it in terms of the sort of the design checks for the PFC I section and the box section design. There is one final section I want to cover though, however, and that's the weld stress calculator in here. Now the weld stress calculator is looking at a more general case of the welds where we've got the angle between the two things that we're welding not being 90 degrees. So if I go back to my drawing here that I've made earlier, it's basically saying that the angle here, what happens when this is not 90 degrees. So when it's not 90 degrees, okay? What do we do? Well, in that instance, we need to use a different diagram over here, and this is replicated on the spreadsheet as well. If I go back, I've got this different diagram here. We need to actually work out the stresses that are being applied onto this throat in here, okay? So how do we do that? Well, what we do is we assume we've got a transverse load up here. We'll start with a transverse load on its own first. We've also got a longitudinal load to consider, but just starting with the transverse load, we basically have this transverse load being applied. We need to decompose this transverse load into a shear stress which is perpendicular to the throat and a normal stress which is perpendicular to the throat. Now this diagram that you're seeing here is actually the same diagram as the 3D view that I showed you earlier. So if I go back to this 3D view here of the weld, you can see that this distance here, that is the throat length of the weld, and you can see that these forces here are the ones that are being decomposed out. So these two forces here were the ones that we just saw on the previous diagram. I've just shown them, this is an end-on view, and this one here is a 3D view, effectively. And the way we do this, this decomposing method, let's go back to this one, is we use some trigonometry here to work out this alpha, and then we use the alpha value to basically work out what our forces are. So if I go back to the spreadsheet a second and run through this, our first section here is just defining our material properties and our thickness of steel. So you can pick a steel grade and thickness. That's going to give us our ultimate limit strength of the material, and then the spreadsheet picks the minimum one of the two materials. So for example, if I had a much stronger material up here, an S355, we're going to get a really high ultimate for the main member, but because I've picked S275 for our substrate, it's going to pick the minimum value. So this 410 value is the minimum of these two cells here. So it always picks the minimum when you're looking at the two materials that you're welding together. So that's what the material properties are doing. This next section here gives you the values you need for working out the strength of the weld. So that's our ultimate strength. This is a correlation factor taken from the Eurocode, and in particular it's taken from this Eurocode here, okay, EN 1993 part 1-8 and the UK National Annex. It's taken from there, and it's taken from table 4.1, and then this bottom bit here is a partial safety factor, and that again is from the Eurocode. In particular, this is from the UK National Annex. So we've got all those bits. The next bit here is where we talk about the geometry and how we decompose our forces into the perpendicular and shear stresses. So the shear stress perpendicular and our normal stress perpendicular. Okay, so we put in our leg length. If I go down here, the leg length again is this dimension here, B. For this spreadsheet, it's assumed that the leg length is the same on both sides of the weld. So we've got a leg length here and a leg length here. If I just draw that again, that's assuming that with this length here and this length here is the same. Okay, it is a bit of a simplification, but it's useful. So that's our leg length, and then we put in our angle between the two members. So at the moment I've got it set as 90, but if I change that to say 60, you'll see this diagram over here change to show that the angle between them is smaller. And to reiterate, the angle is this angle here that we're defining. So we put that in. The spreadsheet will work out the length of our throat, which in this case is 5.2 millimeters. It will also allow us to put in underneath the effective length of our weld and our applied loads. Okay, and these loads will be the transverse load and the longitudinal load. So I can put in say 5 kilonewtons in here, and let's do 2 kilonewtons in there. And the spreadsheet will then basically take this 5 kilonewtons and it will decompose it into the sigma perp and the tau perp. So the shear stress perpendicular and the normal stress perpendicular. And the formulas for that are given up here. So we've got our normal stress perpendicular and our shear stress perpendicular. And we also work out the shear stress longitudinally, and that occurs from this F long value in here. And if I go back to my diagram again, the direction of that is applied in here. Okay, that's the longitudinal force applied to the weld. So once we've applied all of those, we get all of our forces, or our stresses, sorry. So you can see here normal stress, shear stress longitudinally. We combine those with using this formula at the bottom, this formula here. And that tells us, we compare that to the ultimate strength of our weld and make sure that it's passing. Okay, and obviously here it's showing you we're passing. There's also a further check on the longitudinal stress as well, I believe. No, sorry, there's a further check on the normal stress perpendicular to the weld in here as well to do. Normally you're governed by this equation, but sometimes you are governed by this equation at the bottom. And all of these equations are again from this part, this Eurocode here, okay? And this is also known as the directional method within the Eurocode, in case you want to look it up. I've got notes as well through all parts of this spreadsheet which sort of tell you where all these formulas come from if you want to look it up for yourself, okay? So that's what that's doing. The final method down the bottom here, section 6, it actually works out the strength of the weld when you apply your leg length and your angle in here. So basically what it does is it works out all the geometry for you. So it works out your throat length, which is this blue line here, and it rearranges these equations up here, these equations, to work out what force would you have to apply either in the transverse direction or the longitudinal direction in order to just about foul the welds. So if I go down here, you can see here, if I put in 1.268 into my F trans here, hold on a second, I put that into there, and I put in a weld length of 1 millimeters. Oh, apologies. And get rid of that load. So now I've applied, I'm looking at the weld strength here, or I'm applying a load to a 1 millimeter length of weld. Okay, I'm applying the 1.27 kilonewtons, which is this capacity down here, because this capacity is expressed as a kilonewton per millimeter. So by setting up here my length of weld as 1 millimeter and putting in the same force, I'm basically comparing the same two things here. Okay, so I put in 1.268 up here as an applied stress. Okay, I've not put in my longitudinal stress, and you can see it we've reached 100% of the weld utility. And if I do the same thing for the longitudinal capacity, if I put in 1.158, oh, I get rid of the transverse, you can see we're at 100% the longitudinal capacity. So effectively these two capacities are independent of one another. You can't load the weld in both of these at the same time because you'll fail it basically. This is saying that if I apply 1.268 kilonewtons to the weld as a transverse load, that's going to be, the weld's going to be at 100% utility. Okay, that's the capacity of it. And similarly, if I apply just this force longitudinally to the weld, it's going to be at 100% utility. And this is expressed again as a kilonewton per millimeter, which is how it's expressed in the SCI Blue Book. Okay, they give you the welds per millimeter effectively. And just to sort of reiterate on this, I put in the standard weld from the Blue Book. So we're in an S275 material here. I've got a 6mm weld, a weld with a 6mm leg length, 90 degrees, which is what the SCI Blue Book does for all of the welds in that on the tables. I'm going to set that back to 0 again. So I'll go back down here, and we get these two welds are the ones that will appear in the Blue Book. Okay, you get 1.15 and 0.95 for our strength of the weld for a 6mm fillet weld being applied with a transverse or longitudinal load being applied to it. Okay, so this is effectively a more generic way of getting those weld capacities that you can normally see in the Blue Book. Okay, that's all I have time for today. I hope this was helpful, and I'll catch you in the next one. Okay, goodbye.